Hi everyone, welcome back for another video. In this video, I will be solving the Schrodinger equation in one dimension, specifically the particle on a line model. So to get it started, imagine we have some particle trapped on a line of length L that is confined by walls with infinite potential on either side, and inside the well there is no potential energy. So we also have some wave function that describes the wave behavior of this particle. We know it's trapped in the box, so if we would go look for it, it would have to be there. And our goal with this is we want to determine the energy levels of this system and what possible functions are acceptable wave functions. So to do this, we need to solve the Schrodinger equation. It is set up as the Hamiltonian operator acting on psi, which is the wave function, gives back E, or some eigenvalue for that energy eigenvalue, and your wave function. But what is the Hamiltonian operator for this system? H hat. So the Hamiltonian operator in general is negative h bar squared over 2m multiplied by the Laplacian operator. So the Laplacian operator is the second derivative in whatever coordinate system you're using. Are very similar to that, and it's a little bit different in spherical and cylindrical coordinates. If it was 3D, 3 dimensions, but Cartesian, it would be the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. But in this case, or the partials. But in this case, it's just the second derivative with respect to x only. And it's the derivative and not partial derivatives because we only have a wave function that is a function of one variable, x. So if we were to substitute in the Hamiltonian operator into our Schrodinger equation, we would have this. And we need to solve what psi is. We need to solve this differential equation. So let me ask you this. Which functions do their second derivative give you back negative the original function multiplied by a constant? So there are a few functions that come to mind. If we let that constant be k squared, we may be able to see it a little bit better. So the second derivative of some function with respect to x equals negative k squared times that original function. There are a few functions that do this. The trig functions do it, sine and cosine, and e to the ix, or it could also be e to the negative ix works as well. So let's solve this for, if sine of x and cosine of x are both solutions, the sum of them is also a solution. This is the linear combination of both of them. So we will take our solution to our wave function to be a sine of kx plus b cosine of kx. So now we need to think about the boundary conditions. We know that the particle is confined to the well. So the wave function will only be defined inside of that well from an x value of 0 to an x value of L. And it must go to 0 at 0 and must go to 0 at L. So knowing those two conditions, we can then solve our wave function. We can evaluate it for 0. And if we evaluate it for 0, the sine term disappears, and then we're left with b, because cosine of 0 is just 1. But psi of 0 has to equal 0. So with that, b must be 0. And if we apply the other condition where at L, the wave function must be evaluated to 0, we're only left with the sine term at this point. So a sine of k times L must be 0. And a cannot be 0, or our wave function would be 0, which isn't possible. So if we look at sine of KL, where does that equal 0? Where does sine equal 0? Well, sine equals 0 wherever the argument inside of it is some integer times pi. Any integer value of pi would be 0 when any sine of the integer value of pi is 0. So we can evaluate this and get another expression or relation for k. Since we know that k squared, we let k squared equal to 2me divided by h bar squared. And solving from before, we have k is also equal to n pi divided by L. So if we substitute that in for k, we have this. We have n squared pi squared divided by L squared equals 2me divided by h bar squared. This will let us give an expression or an equation for E. We also need to think about something. When we introduced n, we restricted the energy values to discrete values. They can only exist in integer values of n. So between n equals 1 and n equals 2, there are no E values. So what we've done is we've quantified energy. And this is a really important takeaway from quantum systems. We force the energy to exist in these discrete values. So solving for E, we have this. And we can also rewrite h bar, where h bar is Planck's constant divided by 2 pi. In doing so, we can eliminate pi, and we're left with h squared times n squared divided by 8ml squared. And that is the energy levels of our particle in our infinite well. So we're left with our wave function of psi of x equals a sine of n pi x over L. We just substituted k back in it. But what is a? A, by definition, is a normalization constant. And this is an important interpretation of what the square of the wave function is. The square of the wave function is probability density. It is the chance that we would find the wave function at a particular x value. And if we think for a minute, we know that the particle must be confined into the well. So if we sum up all the probabilities from 0 to L, we must get 1. It has to be there. And in this case, we can integrate that. So we can integrate psi of x squared dx from 0 to L and determine what a is equal to. And we're going to do this for n equals 1 because it's the simplest case. So if we write up our integral, evaluated from 0 to L, it must equal 1 because we must find that particle inside the well. Substituting in what our wave function is, we have this. We can factor out the a squared to make it a little bit easier for ourselves. And this is a standard form, and we can look up this integral in the table and we can figure it out. And we could figure out when we evaluate that integral, it's just L over 2. And then when we solve for a, we have the square root of 2 over L. And that allows us to figure out to have every component of our wave function. So if we step back for a second and think about the important takeaways of this model, we have come up with a solution, a wave function that describes the behavior of the particle inside this well. And that wave function was the square root of 2 over L times the sine of n pi x divided by L. We also determined